Good morning, everybody. So, how was your weekend? I hope you had a good one. Actually, it was Easter weekend for the Christians out there. So, hopefully, you had time to relax a bit. And now, let's go back into business. So, last time I guess we started talking about series. Though I think Michael said in the chat that he already finished section 9.4 today. I didn't expect that to be the case, but anyway. So what I'm planning today is to go over some problem from section 9.3, and then probably on Wednesday we'll start working on problems from section 9.4. But if you have questions, you can send them in via the chat. I have already three here from Michael, so I'm going to address them later. But let's just have a quick review of what infinite series are. I guess we started with this meme last time, and we said, okay, have an infinite number of mathematicians. First one orders a beer, the second orders half a beer, the third one orders a fourth of a beer. And the pattern we've seen here is that a mathematician orders half of what the previous mathematician ordered. And the bartender was right here. I guess we had a formula here that says that all he needs to do is to and he will be able to serve everyone, right? So that's one thing about infinite series. Even if we are taking the sum of an infinite number of terms, it seems that we can assign a finite value to, to the infinite sum, right? So we are summing up positive numbers. There are infinitely many of them, and surprisingly enough, we get a sum for them. So this is an example of a geometric series. I think we'll see later some other examples of geometric series as we answer some of the problems that you might have with them. But I guess we also talk about intuitively when does a series converge and when does it diverge. We say that a series is convergent if we can get a finite value for the sum, right? So in layman's term, the series converges if the sum exists as a finite number, and if you cannot get a sum or a value to the summation, or it will go to an infinitely large number, then we say that it is divergent. But there is some ambiguities there, so we provide a more mathematical or a more formal definition of a convergent series. We say that what we can do is to look at the sequence of partial sums. Basically, when we say sequence of partial sums, we truncate the infinite series into the first n terms. So for instance, you're dealing with the infinite series of n going from 1 to, say, infinity. So this means we are doing a1 plus a2 plus a3 plus a4 and so on. Again, intuitively, all you need to do is to take a look at this sum and figure out, will I get a finite number for this? If you get an unbounded value, then you say that the series diverges. If you can get the partials, if you get a finite number, or you can discern a pattern that will give you a finite value for this one, then we say it converges. But there are some ambiguous cases. So to get rid of those ambiguous cases, we impose the following definition. We look at the sequence of partial sums. We mean, look at S1, which is just the first term. S2, which is the second partial sum, so that's going to be A1 plus A2. S3 would be the third partial sum, so that's going to be A1 plus A2 plus A3. So in general, S sub n, or the nth partial sum, is the summation of ANs, n going from 1. Actually, n is not a good notation here. Let me use k here. So it's the sum from n equals 1 until n equals k, all right? And then if the limit of sk as k approaches infinity exists, then the sequence or the series converges. So another way of looking at the convergence of a series is to examine the sequence of partial sums. And that's why we discuss sequences first before series. So if you look at the sequence of the partial sums, then if that converges, then the series converges. and the series will converge to the limit of the sequence of partial sums. Otherwise, it will diverge. So we had some elementary examples last time just to build intuition about this topic. So for instance, we consider the summation of k going from 1 to infinity. We said it is divergent, and it's easy to see because if you expand out the sum, so the first term would be 1. So you plug in k equals 1 until infinity inside the summation. So if you expand this out, it's going to be 1 plus 2 plus 3 plus 4 and so on. And imagine what will happen if you carry on the summation until infinity. You won't get a finite sum. So we say that, okay, this is divergent. And I don't think you will need to write a formal proof about the sequence of the partial sums here because it's straightforward to see that this is divergent. Okay. Now we look at the second example, which involves some ambiguity. So we have summation of -1 to the power n as n goes from 1 to infinity. Okay, so it will just be a bunch of alternating minus and plus ones, and then if we add them together, right? And you might think, okay, I don't know what will happen with it towards in the long run. So because there would be infinitely many of them, right? But if you look at the pattern, you have -1 plus 1, that will be 0. If you add the third and the fourth terms, you'll get 0. The fifth and the sixth, you'll get 0 and so on. So if you do the summation pairwise, you will get zeros, and you might say, okay, if I will take the summation pair by pair, and I'll have just a bunch of zeros, I add a bunch of zeros together, the answer would be 0. But this is an ambiguous case because we define formally, to remove the ambiguity for this particular case, we need to stick to the definition of convergence as the convergence of a sequence of partial sums. So if you collect the partial sums, right, the first partial sum is just the first term, so that's -1. The second partial sum, that would be a1 plus a2, so that's going to be 0. The third partial sum would be -1 plus 1 minus 1. So that's why I got -1 here. Fourth partial sum would be 0. Fifth partial sum would be -1. And that's how we got this. And the pattern here, if you collect the partial sums into a sequence, you get -1, 0, -1, 0, -1. Right? So those are our partial sums. And if we look at the limit of Sn, as n approaches positive infinity, we conclude that this limit does not exist, right? Because it is just an alternating sequence of -1 and zeros, but we don't know what will happen in the long run, right? Or in the end tail of the sequence, we don't know if it will converge to -1 or 0. Actually, it won't converge to any of those values because they will just keep on oscillating. So based on the formal definition of convergence, we say that this series is divergent because the limit of the partial sums does not exist. So we conclude, so the series Sn, n going from 1 to infinity, this is -1 to the power n, diverges. Okay. Now, there are some techniques to show whether a sequence is convergent or not. Of course, you can go directly into the definition, look at the sequence of partial sums, but sometimes that's hard to do. So maybe I should introduce here some of the known series. Maybe we can start with geometric series. Okay, geometric series are of the form summation of r to the n going from 0 to infinity. So be careful here. We are not strict with the dummy variable. That's fine, or the indexing variable, but the starting index of the summation is important. So for the formulas I will write here for the geometric series, it is important that you take note that the summation starts at 0, okay? And then the exponent of r, which is the common ratio, should just be n. So here we call r the common ratio. And then a is just a scaling constant. Okay. And this converges to the sum a over 1 minus r if the absolute value of r is less than 1 and diverges otherwise. Okay. So before implementing any test for convergence, because you will meet a lot of them in this chapter, so try to see if it's a geometric series. Because if it's a geometric series, then all you need to do is to look for the common ratio. And if the absolute value of the common ratio r is less than 1, it would be automatically convergent. No question asked. You just need to mention that it's geometric with common ratio with magnitude less than 1. And if the magnitude is greater than 1, then it will be divergent. Okay. So before implementing any of those complicated tests, see if it's a geometric series first, right? And it would be geometric if you can write it in this form. Okay. What else? What are the other usual series that you have seen? Let me insert the page here. By the way, guys, do you hear me? Do you hear me well? I don't know, but I feel something is off. I don't know what.
Your audio is perfectly fine.
Okay, good. Maybe I'm just feeling something different today. But anyway, all right. So no questions yet. So, okay, good. I don't know, something is odd. I cannot pinpoint what, but at least as far as our class is concerned, everything is good. Have you seen the P series already?
Yes, we have.
Okay, so P series, I guess the proof for the convergence of P series would be the integral test, which is in section 9.4. I won't go into integral test right now. I don't have examples of that in the current worksheet, but maybe it would be helpful if we now put P series in our list. So a P series is of the form 1 over n to the p, and going from 1 to infinity, right? So we start the summation here at 1 because when n is 0, you will have an undefined term, right? So to avoid undefined terms, you start P series at n equals 1. And this would be convergent if P is greater than 1, and it will diverge otherwise. Okay. So here, if you have seen something is a P series, you have 1 over a power of the dummy variable. So P is a constant. You will see like 1 over n squared, 1 over n cubed, 1 over n to the 4th. So those are P series with different values for P. All you need to look for is the value of P. If P is greater than 1, it's convergent. If it's less than 1, then it would be divergent. If P is equal to 1, it is also divergent, which is a special series. We call it the harmonic series. This is summation, and going from 1 to infinity of 1 over n. It's what we call the harmonic series, and this is divergent. No questions asked. 1 over n is divergent. Okay. What else? Well, we also have telescoping series. These are series which is better analyzed looking at the sequence of partial sums. So we say it's telescoping series because, well, you can write it as a, how can I write it well? An example would be, say, a sub k minus a sub k plus 1, k going from 1 to infinity. And then if you expand this, so this is an example, though it's not a general form. We'll see later some examples of telescoping series. But the idea about telescoping series is if you expand the first few terms, like say, so if k is equal to 1, we'll have a1 minus a2. So this is the first partial sum. The second partial sum is S1 plus, what's the value when k is equal to 2? We get A2 minus A3 plus when k is 3, we get A3 minus A4 and so on. But you see that some of the terms will actually cancel out. So you have negative A2 here, positive A2, they will cancel each other out. Minus A3 over 8, then plus A3, they will cancel out. And then this minus A4 will be canceled by the next A4 there, and so on. So that's why it's called telescoping series, because some of the middle terms will cancel out, leaving you with the first few terms and the last few terms. So it looks like a telescope wherein you can, even if you're looking through one lens, you can see an object that is far away without the intervening distance between. So some of the middle terms will cancel out, and to determine whether a telescoping series converges or diverges, you need to look at the sequence of partial sums. So look at the sequence of partial sums. Okay. And then to close this discussion of the basic test for convergence or divergence, maybe I'll put down some theorems here. So we have, say, I'll just put them in layman's term or in easy terms so that we can remember them better. But if you want the details or the formal statement of these theorems, you can look at the textbook. But first, if you have a convergent series plus convergent series, it is convergent, okay? And they will converge to the actual sum. So if you have a summation of two sums, that means if you look at the individual series, if they are both convergent, then automatically the sum is convergent. And they will converge to the sum of the individual series. On the other hand, if you have a convergent series plus a divergent series, this is divergent. Okay, convergent plus divergent is divergent. The other cases, we don't have any conclusion. Actually, there's only one remaining case. Divergent plus divergent can either converge or diverge. So there is no conclusion if we have divergent plus divergent. Okay. Now, another example is if we have a constant times convergent. This is convergent. It is easy to see why, because if you have a convergent series, right? So say if you have summation of an, if this is convergent, so if you multiply it by a constant, right? That constant can come out of the summation as a c there. So that means if you get a finite summation of an, then you multiply it by a constant, then that will also be convergent. Similarly, a constant times a divergent series is divergent. So, okay. Again, it's easy to see why. So if you cannot get a partial, if you cannot get a finite sum out of a series, no matter what constant you multiply to all the terms, you won't get a finite sum still, right? Okay, what else? Okay, maybe final remark. If two series differ only in the first few terms, then they both converge or they both diverge. So this is basically a simple comparison. If you can write a certain series and it looks like sort of another known series with a known convergence or divergence, but they only differ by the first few terms, then they will have the same property. They will either both converge or diverge. Okay. So now let's look at some examples. Let's see. Oh, by the way, before we go to infinite series, do you guys have some questions about problems like 15 to 18? Do you want us to try some of them, or you're perfectly good with this? Because basically this is just using properties of summations and applying formulas.
Could we try the second one on the top towards the right?
You mean this one?
Top.
What number?
It doesn't show the number. That's the weird part. It's the one that's like n times n plus 1 times 2n plus 1 over 6.
Oh, you mean this one?
Yeah.
Oh, this one actually, the top row, these are the formulas that you can use.
Oh.
Yeah.
Okay.
Yeah, but I know what you're saying because there's a proof for this formula saying how this was derived. But I don't think that's in the scope of this class because the proof of this formula or how you get this formula is using what we call the principle of mathematical induction. I don't know if you tackled that in the lecture, but I don't think that's part of the coverage of the class. I can discuss it, but that's extra material. So, but maybe let's reserve that for later.
Yeah.
But let's see.
I'm sorry. I didn't see that it was a formula. I just thought it was like one of the problems.
Yeah, no worries. Yeah.
Mm-hmm.
Let's try probably problem 16. And yeah, just to show you how this problems work. So let me copy this. Okay, let's try this here. Okay. I copied everything because I hate memorizing formulas. So some of this is not it's not familiar. It's not familiar to me. So I need to look at them. So let's try problem 16, for instance. So for problem 16, we are looking for the sum from k from 1 to 12 of 2k squared plus k. So here first we note that I will try to use the formulas out of here, right? So basically the idea here is I want to write this summation in terms of a combination of the left-hand sides of the top rows or the formulas given in the problem. So, but before I do that, maybe it's nice to note here what the value of n is. Here the value of n is 12, right? That's the upper index of the summation because if you look at the formulas, their upper indices are all n. So basically, if you'll follow the formulation of these things, n is equal to 12 because that's our upper index here. Then before I'll be able to use these formulas, I need to use some properties of summation here. First, I can sort of distribute the summation into the two terms. So I can expand this out as summation from 1 to 12 of 2k squared plus summation from k equals 1 until 12 of k, right? So this is the additivity of a summation. You can you can take the sum of individual terms into separate sums, okay? And then I'll use the scalar property or the scalar multiple property. If there's a scalar, a common scalar inside the terms, then that scalar can come out of the summation. Just as like as what we used to apply for integrals, right? So 2 will come out, leaving us with a summation of k squared, k from 1 to 12, plus summation from k equals 1 to 12 of k. Now, here is where I will use the formulas given in the problem. So I am here. I'll copy the 2 down there. And then I'll look for an expansion, or what is a simplified version for sum of k squared, k going from 1 to 12. If I look at the formulas given, look at the second formula. That gives us the summation of k squared, right? So it says there that the summation of k squared, k going from 1 to 12, is equal to n times n plus 1 times 2n plus 1 all over 6. But for our specific problem here, n is equal to 12. All right. So that means the sum, the first summation, will simplify into 12 times 13 times plug in n equals 12 here. So we'll get 2 times 12, 24 plus 1, that's 25 all over 6. Okay. And that would be the summation of k squared. Then we go to the summation of k from 1 to 12. We'll just use this formula, the summation for k. So this would be plus. The summation is 12 times 13 all over 2. And if you evaluate this, you simplify. Let's see if this simplifies well. 12 and actually it's a big number, so I'll just keep it like this. So it's up to you to simplify. Everything that will follow is simply arithmetic, so you can either use a quick calculator or do this by hand. Okay. So I guess the other problems can be solved similar to this one. So you just need to first apply properties of summation in order to write some parts of the given problem into one of the 4 forms given in the formulas here. And once you have them written in the forms given in those formula, you just need to replace the value of n by the specific n in your problem. Okay. Any questions? Is that good? Do you think you can try problems 15, 17, and 18? Or do you want one more?
One more, please, if it's not too much of a hassle.
Sorry, Daryl, what's that?
I was just asking if we could do one more if it's not too much of a hassle.
Oh, sure, yeah, no problem. So what do you think would be more interesting?
So I think 17 would be pretty easy with the formulas. What about 18?
Okay, good. Nice choice, 18. Because for 18, it is not yet written in the usual summation notation. So basically here, the preliminary step is to write it first in summation notation. So we have problem 18. We have the sum from 1 plus 3 plus 5 until 99. So our goal is to write it as a summation of expressions involving k from 1 until some value, right? So let's look at the pattern. So what's the common characteristic of the numbers in our summation?
They each increase by 2.
They increase by 2. Okay, what else?
They stop. It's not infinite, right? So it has a
yeah, it will stop at 99. Well, a little further to what you said earlier, that they increase by 2, right? Because you start at 1, then you get 3, then 5, and then 99. I would like to say that, what I'm looking for is that they are all odd numbers, right? And then we have a general formula for writing odd numbers. Odd numbers can be represented as either 2k plus 1 or 2k minus 1, right? So because 2k is even for any value for k, if you add 1 to it, you get something that is odd. Or to get an odd number, you start with an even and subtract from it a 1, right? But let's see which one is appropriate to put inside our summation here. Is it 2k plus 1 or 2k minus 1? What do you think?
I think it's 2k plus 1 if we want even numbers.
Well, I still want odd, but I'm sure that what will go inside my summation would be either of these two, right? But I need to be careful because look at the formulas again. The formulas that are given to us starts the summation at k equals 1. And when k is equal to 1, we should get 1. When k is equal to 2, we should get 3. When k is equal to 3, we should get 5, and so on. So which of these two guys will give me that particular ordering?
The bottom one. I see now.
Yeah, the bottom one. Oh, will it be the bottom one? Oh yeah, it would be the bottom one. It's going to be 2k minus 1, right? Because in 2k minus 1, if you plug in k equals 1, we get 1. That's the first term. When k is 2, plug in 2 here, we get 3, which is the second term. When k is 3, we get 5, which is the third term, and so on, right? And then the next thing here to find out is what is the upper index? The summation starts at k equals 1 and will end where?
K equals. So it has to be something that would equal 99 if multiplied by 2. Would it be like 50?
Great. So it's going to be 50 because if we plug in 50 into here, we get 2 times 50, 100, minus 1, 99, and that is the last term. And then we're good. Okay? So it's like playing a puzzle here. You need to look at the pattern. And then once you get the summation notation, we again use some properties of summation, in order to write it in the forms given in the formula. So I can again distribute the sum into the two terms here. So I'll get summation of 2k, k going from 1 to 50, minus summation of 1 as k goes from 1 to 50. Good. And then again, I can take out the scalar multiplier outside of the sum, minus summation, k going from 1 to 50 of 1. All right. And then now what happens here? We have 2 times summation of k, but summation of k according to the formula is just n times n plus 1 all over 2. So here our n is what? Our n is 50. So it's going to be 50 times 51 all over 2, right? That's n times n plus 1 all over 2, minus, what is the summation of 1 from 1 to 50?
50.
Great. It's going to be 50. Oops. Because here you're just summing up a bunch of ones. How many ones are there? There would be 50 ones, right? So the total is 50. So this would be your final answer, or whatever this number simplifies to, right?
Okay. Thank you. That makes sense.
Okay. So you just need to break this down, look at patterns, and then apply the formulas, right? Actually, just a fun fact, legend says, or a common story says, though I'm not sure if this is true or not, but they said that this formula was proven, though I'm sure this was known to early mathematicians like the Greeks and so on, but the first formal proof, I guess, was provided by Gauss way back when he was in his elementary days. I think he is he's about he's not even 10 years old when he proved this formula. And the story goes that his teacher tried to punish him and told him to sum up the first 100 numbers. So take 1 plus 2 plus 3 until 100. And after a few seconds, he stopped and he said he knew the answer. And he used this formula, and his teacher was quite surprised because he provided a nice, elegant proof. So, and then that's something that he discovered back in the 16 or 1800s, and yet here we are still using them. Okay. All right, let's see. What are the other problems here? So I guess that's fine. Looking which ones would be nice to answer. Let's see. Let's try problems 25 to 42, because what we will do in or maybe 19 to 24 is not also bad. So let me think a bit. Which one would be nice? I'll try 25 to 42. Some problems from here. Let's see which ones would be interesting. Oh, by the way, I forgot to mention one important test for convergence. Aside from this, guys, I forgot to mention the basic test for divergence. Now, this is aside from identifying if there are special series involved, one thing that you can try first would be to check whether the test for divergence applies. So this is, I think, the basic test for divergence. So if you have the summation of an and going from 1 to infinity, if the limit of an as n approaches infinity is not equal to 0, then the series diverges. Okay, let's see why this makes sense. So you're summing up a bunch of ANs, an infinite bunch of ANs. If in the long run the ANs will not go to 0, then automatically the series diverges. And it's not hard to accept this as an intuitive fact, because if in the long run you are getting numbers that are not equal to 0, they might be big numbers, there might be small numbers, but the thing is they do not converge to 0. That means you keep on getting terms that are greater than 0 or less than 0, and there are infinitely many of them in the long run. So automatically you cannot get a finite sum. Okay. So this is one easy test to see. If you look at the terms inside your summation, you take the limit. Usually taking the limit of ANs is not that hard to do, right? At least mentally. If the limit is not equal to 0, then automatically the series diverges. But if it is equal to 0, no conclusions can be made. You need to look for another test. So maybe I should put that here as a caveat. But if the limit of an as n approaches infinity equals 0, then no conclusions can be made here. So you need to make sure to try another test. Because if the limit is 0, it can be convergent, it can be divergent. So for instance, remember the harmonic series 1 over n and going from 1 to infinity. If you take the limit of 1 over n, as n approaches infinity, it is equal to 0. So that means in the long run, you get addends that are closer and closer to 0. In fact, the last terms or the terms in the tail end of the series will go to 0. And yet this is divergent, right? This is the harmonic series, which is convergent. But remember the p series 1 over n squared? And going from 1 to infinity, this is a p series with p equal to 2. The exponent is 2, greater than 1, so it is convergent. It is convergent, and the limit of 1 over n squared as n approaches infinity is also 0. So here we get two series whose n terms both converge to 0, but they do have two different behavior. You have a question, Daryl?
Oh, you already answered it. I was just going to verify that the harmonic series is always divergent, but you just okay.
Yes, it's always divergent. Which probably, if you remember, during the hype with the movie Divergent, Divergent, they have these posters or memes showing the harmonic series 1 over n. So okay, but anyway, let's see some examples here. let's start probably with problem 29.
After that one, can we do 36 if there's time?
Yeah, sure. Maybe I can go to 36 because they will just use the same principles. Yeah, but 36 is much more interesting. Good choice. Let's try 36. Okay. Now, if you take the limit as k approaches infinity, though it's not that obvious, but the limit will be equal to 0, so that basic test for divergence will fail. And then but actually even prior to trying the basic divergence tests, you can first identify, does this look like one of the basic series that we have enumerated earlier? Obviously, it is not harmonic, right? Because harmonic series doesn't involve exponents. It is not a P series because P series has a constant exponent, right? So, but if you notice, this could be written as a geometric series, right? Because you have an exponent that involves k, and then there's just some constants that we can play with. Yeah, Herson, that's correct. It would be a geometric series. Okay. Now, but before we can conclude anything, we need to write it in the proper form of a geometric series. Recall that a geometric series is of the form summation of AR to the n going from 1 to infinity, n going from 0 to infinity. So geometric series. So that's what geometric series are. So let's try to write it in terms of these. Oh, but first thing, the dummy variable is k. So I'll just replace the dummy variables by k. But it doesn't matter, right? So everything's good as long as you're consistent with the dummy variables. So here I need the summation to start from 0. Maybe I'll try to do that second. I'll just first try to manipulate the terms inside the summation to write it as AR to the K, AR to the K or something like that. So here I can have it as what? So first I can write it as well, I can write it as 3 to the what would be a nice way to write it? Well, I can write it as 3 to the k over 4 to the... I'm looking for a nice way to write it. Maybe I'll have 1 over 4 to the negative 1 here. And then I'll have 3k over here. Okay. And then I can further look at this. I'll apply loss of exponents. So I can write, this is 4 to the third to the k, right? So I'm just grouping like terms here. Because here the loss of exponents says if you are raising a power to another power, you simply multiply the exponents. So this guy simplifies to 4 to the 3k. And then I have a multiplier 4 to the negative 1 over here. So I'll go back to the original denominator. Good. And the summation here goes from 2 to positive infinity. And then here I can further write it as summation of 4. That's what this guy will simplify to, right? Times 3 over 4 cubed. What is 4 cubed? I think that's 64. So that's 4 times 4, 16 times 4, 64. Raised to the power k. K going from 2 to positive infinity. Okay, good so far. So at this point, you can actually conclude right away that this is a convergent series because it's a piece, this is convergent since it's a geometric series. with common ratio r equals 3/64, right? So r is whatever is the base of your power k. Here, 3/64, and obviously that is less than 1. Remember our criteria, if the absolute value of r is less than 1, then it's automatically convergent. Okay? But looking at the sum is a different thing, because we say that the sum of the geometric series is actually equal to a over 1 minus r. But that sum or this formula holds true only if your starting index is k equals 0. Okay? So here I need to be careful. I need to write it first as a summation that starts at 0. So I need to adjust the index of summation. Okay? Now, what did I do to go from here until here? Well, I decreased the starting index by 2. So if you decrease the starting index by 2, you need to increase the dummy variable by 2. Right? So this would be k plus 2. All right. How do you check if what you did is correct? But I hope this is intuitive, because here we are supposed to start at 2, but here we want to start at 0. So what I did here is to decrease the starting index by 2 positions. So that means all the dummy variables inside the summation should be increased by 2. So a quick check, the first term here will be k equals 2. So 3/64 will be raised to the second power. That should also be the first term here. But the first term using this summation starts at k equals 0. Plug in k equals 0 here. The exponent is 2, which gives us the same starting term. Okay, so this adjustment is correct, right? Now we can apply the summation. Oops, but before that, remember that the exponent for the formula to work should start at k, should just be equal to k. But here we got k plus 2. So in order to get it in the right form, I need to factor out 2 of the 3/64s. So I'll have 4 times 3/64 to the second power times 3/64 to the k. So at this particular point, we can observe that our a is actually 4 times 3/64 squared. And so remember, the formula for the sum is a over 1 minus r. So we already knew that a is 4 times 3/64 squared, 1 minus r. But we already knew that r is 3/64. And there you go. That would be the sum of the geometric series. So a little bit more work is required if you want to get the sum, because you need to make sure that you get the actual value of the summation by comparing it with the formula given. But if you're simply asked to determine whether it is convergent or not, at this point, you can conclude that that is the case by just looking at the common ratio, which is less than 1.
Okay, thank you.
All right. Okay, yeah, let me go to Michael's question. Let me see. Okay, I guess this answers the second problem that you sent, Michael. So I hope that's fine. You can do the similar thing, though your second problem is much easier than what we answered here. So I hope you get that one. Your first question is an example of a telescoping series. So here his problem is, let's call it second problem. Summation k from 2 to infinity of 5 over k squared minus k. Now, this will not fit into any of the special series that we have seen earlier or that we have listed earlier. So if you have a fraction over here, what I suggest is try partial fraction decomposition, okay? So note that 5 over k squared minus k can be written as 5 over, let's factor the denominator. So we have k times k minus 1, right? So partial fraction will still haunt us until this chapter. So remember the partial fraction decomposition? The factors are k and k minus 1. Both are linear. So in an expanded form, this will look like a over k plus b over k minus 1. And what we need to do is to look for the values of a and b. But the same principle will apply as what we did in the previous chapter, though they are in two different contexts, but you can use the same technique. So if we multiply both sides by k times k minus 1, we get 5 equals a times k minus 1 plus b times k for all k. And then give specific values for k. Let's use the Kähler values. K equals 1 will give us 5 equals b, while k equals 0 will give us 5 equals negative a, or that means a is equal to negative 5. So our original summation, starting from 2 to positive infinity, of 5 over k squared minus k, actually can be written as the sum from k equals 2 until infinity of the partial fraction decomposition. So we get negative 5 over k plus 5 over k minus 1. Or I can rearrange some of the terms, then factor a 5 out. I can have 5 times summation from 2 to infinity of 1 over k minus 1 minus 1 over k. Right? So I just factored out the 5 and then rearranged the terms inside the summation. Okay? Now, this is of the form of a telescoping series. If you remember the form of the telescoping series I gave you earlier. Now, for telescoping series, as I've suggested, you try to look at the first few terms, right? So the first partial sum, S2. I'll use S2 because the summation starts at k equals 2. S2 will just be 5 times, when k is equal to 2, we'll have 1 over 1 minus 1/2. Okay. And then S3 would be 5 times this guy plus, let's plug in k equals 3 here to get the second term. So we'll get k equals 3 will give us 1/2 minus 1/3. And then if we look at S4, we'll get, so we'll do this until you see a pattern, right? I guess after S4 we can discern the pattern here. S4, I'll plug in k equals 4. I'll get 1/3 minus 1/4. And then what do we notice here? Well, the minus 1/2 will be canceled in S3, leaving us only with the first and the last term there. In S4, minus 1/2 plus 1/2 will still cancel each other out. Minus 1/3 and 1/3 will still cancel each other out. So that leaves us again with the first and the last term. Okay. Now, in general, if you continue on, I hope you can see the pattern out here. We have a constant 5. And then it looks like 1 will always be there, 1 over 1. It won't be canceled by any of the terms. So that looks like a mainstay. And then based on the pattern here, I'll notice that, okay, it seems that there are only 2 terms left, right? After the cancellation is done. What will be left here is a minus. Look at this. I have minus 1/2. I have minus 1/3. I have minus 1/4. So if I am on the nth partial sum, what do you think will be here?
The nth term.
Yeah, the nth term, which would be what? 1 over... yeah, Michael, it's 1/4 at S4. But if I'm looking at S, let's call it SK. If I'm looking at the K term, what will be left here? So let's see the pattern. At S2, I have minus 1/2. At S3, I have minus 1/3. At S4, I have minus 1/4. So if I have SK, what do you think will be here? Yeah, Arsalan, you're correct. This would be minus 1 over K, right?
Okay.
Because when K is 2, we have minus 1/2. When K is 3, we get minus 1/3. When K is 4, we get minus 1/4. So when we have K, I'll have a minus 1 over K. And remember, we said that the series converges if the sequence of partial sums converges, all right? So this is our kth partial sum. So if we take the limit of the kth partial sum, we're looking at the limit of 5 times 1 minus 1 over k as k goes to infinity, right? And then this would be 5 times 1 minus, but as k goes to infinity, 1 over k will go to 0. So the answer here is 5. So the sequence of partial sums converges to 5. So therefore, the summation of 5 over k squared minus k, was that the given? Yeah. K starting from 2 to positive infinity will be equal to 5. So it converges because we get the finite answer. Okay. Yeah, unfortunately, it's already 6 minutes after the time, and I have another class to run to.
Before you go, Neil, could you re-explain like the 5 times parenthesis of 1 minus 0?
Oh, this one? Yeah, I'm looking at the limit, right? So I'm looking at the limit of SK. We knew that SK simplifies to this guy, right? And then in limits, this 5 can come out of the limit. So that's how I got the 5 in there. Good.
Yes.
And then I'm looking at 1 minus 1 over k. What will happen to it as k approaches infinity? Well, 1 will remain 1. There's no k in there. So just write it down in the next step. But what will happen to 1 over k? K goes to infinity. So 1 over infinity is 0, right?
Oh, okay.
So that's 1 divided by a large number. That will go to 0. So that simplifies to 5.
Okay. Thank you.
Okay. Right. I hope Michael is still around. Just a clue for the third question that you sent. Yeah, this will diverge because this is a multiple of the harmonic series. But when you plug in n equals 1, you get 4. N equals 2, you get 2. N equals 3. N equals 4. N equals 5. Okay. Now here, the problem with your answer, Michael, I hope you're still around, is that you took the first 4 terms of the series. So you just plug in n equals 1, n equals 2, n equals 3, and n equals 4 into the AN. But you're looking for the first partial sums, the first 5 partial sums. So your S1, the first partial sum would be 4. S2 would be 4 plus 2. S3 would be 4 plus 2 plus 4 thirds. S4 would be 4 plus 2 plus 4 thirds plus the 4th term, and so on. Because you were asked to list down the first 5 partial sums and not just the first 5 terms in the series. Okay? But your idea is correct. It is still divergent because it's a multiple of the harmonic series. Yeah, just be careful because the terms here are easily messed up. So be careful. All right. So I have to run, guys. Thank you for coming today, and then let's see each other again on Wednesday for more examples. All right. Bye, guys.